Good afternoon, everyone. We are organizing a 1-hour science webinar on two data sets that have been produced by people here listed on the slide, Leandro Parente, Yu Fong, and Maria Hunter. And they are connected here with us, and Maria is connected all the way from Brazil. So we will, let me look at show you the program. We will do two seminars. One is on the production of the global ensemble DTM, presentation by Yu Fong Ho, our researcher at OpenGeoHub. And then the second talk we'll hear from Maria and Leandro about production of global median vegetation height of the world. Both products are 30-meter resolution global products, and we will video record this webinar. And if you miss something, some important information or link, you can watch a video. It will be published on the TIB channel under the OpenNet Monitor Science webinars. I should also mention the both works. There are extensive technical documentation about both presentations, and I mentioned the two preprints here. I just want to emphasize these are preprints, so they are still under review. One publication already we got the reviews back, and luckily it's a positive review. So we hope soon that the publication will be available online. And then the second one we are still expecting the review. I should mention the work's been funded, especially the work on producing global ensemble DTM has been funded on the Earth OpenNet Monitor project, which is the Horizon Euro project running until July next year. And then we also, this vegetation, median vegetation height mapping is output of the Global Pasture Watch Consortium work, project called Land and Carbon Lab, which is led by the World Resources Institute, and with a number of organizations listed here. And the Global Pasture Watch is producing a suite of products, usually annual or bi-monthly products, and covering 2024. Currently, we have only until 2022, but we are just updating the maps to 2023-24. And we're producing different things: grassland extent maps, livestock, short vegetation height maps, grassland productivity. And with this thing, I would like to pass on the slides to Yu Fong Ho to tell us about production of the global ensemble digital terrain model. Please, Yu Fong, floor is yours.
Hello, everyone. I'm Yu Fong from OpenGeoHub. Today, I'm going to present my work about Ensemble digital terrain model and the derivations. Meters. We're using multi-source of data, including also spectral LiDAR from ISAT and JEDI, and we were kind of diving into so more introduction about LiDAR data. So nice slide, please. So okay, this is we first started in the introduction. So first, we are measuring the canopy height or terrain height. This kind of like a height measurement. How we could do that, and it's actually have multiple instruments. But now we are including this instruments called LiDAR, which is using the light to distance to actually measuring the distance to calculate the height of any objects. And it has been used in cars and using like auto driving also. And here we are mainly talking about how we actually estimate the object height on our surface. So from the individual objects, we have mobile LiDAR or terrestrial LiDARs that can measure the height of the individual objects. And to the defined region, for example, like agricultural fields or sanitary or like a city level, we can use our UAV LiDAR to actually have those objects that can be mapped. And to upscale to the level, we have the urban LiDAR, which is well used for the national to actually measure the height of the national and regional area. And the topic level is the topic of today, spaceborne LiDAR. which is orbit around the whole globe to actually measure the height of the global surface. Next slide. And one of the spaceborne LiDAR is called JEDI. The full name is the Global Ecosystem Dynamics Investigations, which is the former LiDAR. It started with 2019. You have like about 4.5 billion points so far until 2023, and the coverage latitude from 51 south to 52 south to 52 north, and storing the point geometric. And this instrument attached on the International Space Station. And this is the on the left side, you can see this is actually the International Space Station, and LiDAR instruments is attached on here, and then you actually use for mainly mapping the tree, and you have the waveform of the terrain height and also the canopy height. Next slide. And this is one of the examples that when we investigating this product, we can clearly see on the right side it's with the LiDAR instrument goes through the forest. They can actually map the top of the canopy of the forest and also the terrain height were two kind of like peak of the waveform. And the left side is the open area. And unfortunately, this is the product that was designed for forest canopy height. So when you do like open vegetation, you only have kind of, if you have a sparse tree, you only can detect the very terrain height and hard to actually record the height of the tree because of the limitation of this instrument. Okay, next. And another spaceborne LiDAR is called ISAT-2. ISAT-2, the whole name is Ice Cloud and Land Elevation Satellites. As in name, the ISAT is usually they used to be mapped for like measure the height with the iceberg to actually know how the global warming impact of our ice. So they'll have the global coverage up to 90 altitude and minus 90 south and 90 north. And he also operates similar time in 2018, have 25 billion points so far to 2023. And this is the product that we are going to introduce. And they also have the point geometric. And on the right bottom side, you can see this is actually the cross section of how ISAT measure the surface. So you have a lot of photons that can penetrate or arrive on the ground, and they have been reflected when you get from the top of canopy, also in the middle of the canopy, but also the ground surface. So the cross section can see that on the top of the light green was the top of the canopy, and the dark green is actually the middle of the canopy, and the brown dot is the terrain height. So that's basically tell you how this ISAT they try to orbit around the Earth, how they actually measure the height when they cross over. Okay, next one. And for the ISAT, have if you open up the data, you can see that they actually have multiple layers of the information. First, you have the reference ground track, and each ground track you have 6 ground tracks. So when the ISAT pass through the ground surface, it actually has 6 ground tracks, like 2 in pair that measure together, and to compose to have 6 tracks that kind of scan through the surface. And in each track, you have 100-meter segments, and in each 100 segment, you have 20-meter segment for each. You have 5 20-meter segments and 100-meter segments. And the middle side is that an example. The blue point is in the photon level, and the brown point is the actual estimate of the land and vegetation metrics from the product that ISAT-2 produced for ATL08. And the ATL08 is processed from ATL03, which is they use this kind of like photon information to aggregate into the measurement of canopy and terrain height. And next slide. And since we are understand a little bit of what they are measuring, we have to go into how can we use this data to actually modeling our land surface height, or in my use cases, the terrain height. So this is actually the spaceborne LiDAR data, how they orbit around the Earth. They are not like taking, they are like actually very thin strings that when they orbit around Earth, because LiDAR has very high frequency, so they cannot measure too wide of the surface. So they actually have this kind of string line every time they orbit around the globe, and throughout the time they slowly capture all of the surface based on their orbit. Okay, next. And how we first do is we do the spatial temporal blocking, because the original data is actually organized by the orbit. But in orbit, it's hard to actually locate at one position, have to see that how many JEDI point or ISAT point has been in one single spatial temporal block. So the first thing we have to do is to reconstruct it, this kind of spaceborne LiDAR into the spatial temporal blocks. And this is an example of the JEDI. So we do using the algorithms of Parquet to do the partition and get a spatial temporal tile, like 5 degree tile yearly, to actually reorganize this data. So next one. And after like we process the data, we can know how spatially or spatial temporally how many data we have in each block. So this is an example of ISAT and JEDI, how many points in each small block has for us to use for further modeling. And I was already organizing the JEDI point in the stack, but so you can open this open land map to actually access the JEDI catalog. And ISAT2, we are the catalog of ISAT2 are still under construction, but the data will soon be open under CC BY license. Everyone can just also use this data to map what they are interested in. Okay, next one. And after talking about the spaceborne LiDAR, we also have we're slowly diving to mapping the global terrain model. But if you see of this website, Open Topography is actually the open data set website that record all of the digital elevation models. So you have SRTM here, you have NASA DEM, you have Globe 30 Copernicus, and ALOS from Japanese space agents. And they have multiple different digital elevation models, but why we are still going to map. Next one. So so basically, if you are not familiar with that, there's a paper that talked about the terminology about the digital elevation model. So basically, there's two types of digital elevation model. One is the digital surface model. One is digital terrain model. And the terrain model is actually estimates the bare ground of the Earth's surface, and the digital surface model contains the height of the tree and also the buildings. So that is the difference. Most of the let's say all of the digital elevation map that it's fully open, like ALOS, Copernicus, they are surface models. So they don't really find the terrain surface that were mainly useful for example, hydrological mapping or soil mapping, this kind of application. So that is why this is necessary for us to generate one fully open terrain model. And to model the global terrain, what we can use is to incorporate all this digital elevation model with some of the auxiliary layers like vegetation objects modeling, like canopy height model, tree covers, and also artificial object model, because we also wanted to map out the buildings, and also some of the accessory data like hydrospectral images like NDVI or NEWI, which is related to vegetation or with human settlement. And we are trying to see that if we can use this data to map the terrain, which can be observed by the instrument that we just mentioned, the spaceborne LiDAR. So we try to incorporate this concept using a simple random forest model to map this. Okay, next one. And leverage on what we had in our spatial temporal blocking, we developed this methodology. So basically, we split the modeling into two steps. One is the global modeling. So the global modeling is a sample from using the stratification of the landform and object height. So you have like a global representative of different type of terrain and also different type of tree and buildings in different type in all throughout the whole world. And we do the global tuning and modeling. So we get like a first global model, and this global model will enter into the local tiles. And in the local tiles, we will query more points from the local area to get more information, local context into this model, and do a fine tuning in the local tile and predict this global to local model to have a prediction of the whole world. But actually, all the predictions have the generalizability of the global context, but also adding extra information at the local context. Okay, next one. And let me show some results. So this is the Ensemble digital terrain model, 30 meters. We have a nodal link here, and you can access here to have this high resolution data in one single file. In the next, and this is like the big pictures of how we actually predict this global ensemble digital terrain model. So we have create the tile that we have mentioned for local tiles, 1,000, 2,000, 2,000 pixel, and we have 1,157 tiles. And because some of the tiles we don't have a spaceborne enough spaceborne measurement that happen there. For example, in the tile that marked red, they are, for example, the tiles cover some Pacific small islands, so they don't have enough spaceborne measurement of that. So those data have no extra local model, but we still use the global model to predict the terrain height. And this is how we run this model. Next one, in practice. And this is the showcase of how this actually helped to improve the local accuracy. So this is the graph that we are extracting from our data. So the left is the global model, and the right is the global to local model. So we can see that the local context actually helps to improve the local accuracy. Okay, next. And this is also one of the results that we have to see that actually remove the buildings and also the forest. Next one. And we also predict one uncertainty map alongside with the terrain prediction. We are this is why we quantify the standard deviation by using different the number of the nodes from the reference forest to actually derive the standard deviation from that, and we'll also map this. And we found out that this terrain uncertainty is associated with slope and the tree cover, but this is like a brand new product that no one ever produced, and we are also welcome that people to investigate on this product and to see that how can we dig out what is actually associated with terrain predict uncertainty. But yeah. And we also compare with current other global terrain models like FABDEM, MERT, DTM, and FETEN-DEM, using the independent reference digital terrain models. And the link is linked to this kind of reference terrain models. But this data also be used in multiple comparison of the digital terrain models of the world. And we can see by sight our global ensemble DTM have relatively good results compared with FABDEM, but the FETEN is actually also good to predict the terrain. And the right side is from the lens use land cover, and yeah, our result is also quite comparable with the state of the art digital terrain model. Okay, next one. And we also, alongside with the terrain model in our research, we also produce 15 land surface variables. And this is one of the example of the hill chain that we introducing more. Next one. And in addition to only 30 meter, we also produce this kind of multi-scale terrain derivations into 6 scale. And the case showing here is the slope in degree and the specific catchment area in Hualien of Taiwan. And this is the showcase of the 6 scale. We have 960, 480, 240, and 120, 60, and 30 meter resolution. To see that actually you see on the right side, as the resolution increase, you can clearly see that the big channel has divided into smaller channel. And using this kind of concept, we can help to actually map, for example, soil type or different kind of soil property, because in different scale, they provide like different detailed information that add up to be a more comprehensive for each pixel. Okay, next one. And we also compare our data with the state-of-art hydrologic data. It's the data set produced by Giuseppe in 2022. They mapped the hydrologic 90 meters. The paper is the new high resolution global hydrological data set, which is using MERT to derive. But we push a little bit of the boundary to using the more advanced computation infrastructure to create higher resolution and also more efficient computing. Okay. And you can find, so this is all of the result we have shown, but if you want to know more, you can find the data set in our Zenodo. Next. And this is, you can open your QGIS easily. And this gives show, you just copy the link and you open the your QGIS and pass the URL, and using this kind of add raster, and you can already add this 30 meters global data into your local QGIS, because there's organizing the cloud optimized format. So you don't have to worry about you will crash your browser or you will crash your software. Okay, next one. And we also appreciate a contribution and also an open reproducible approach. So we already have some issue that people spot in our product. So you can also come here. If you can also take a look at the data and you found some problem, you can also report the bug or any type of issue, register here, and we can actually actively solve together. Make the product better. Next one. And the next step, what we are going to do in this project is the first improve the global Ensemble digital terrain model. So we have already discussed in the community that we will try to have more advanced mapping technology, for example, using hybrid transformer for like high modeling. And also a more community-based approach to map with the national DTM to improve the accuracy in certain places. And also we are working on creating an open framework for individual local improvement. So a kind of like a systematic approach using the cloud infrastructure and the federal learning to improve the data. Then everyone is welcome to join and contribute, and also be kind of appreciated by contributing and also using this data. And for the land surface derivative, oh, I haven't finished. Sorry. For the land surface derivative, we will have receive some comments and try to increase the number of variables. For example, already like some organization, they are interested in more hydrologic layers, and we are planning to have the next version to create more layers to serve a wider community. Next. And to recap our presentation, first, we talked about the spaceborne LiDAR, that they have a wide range of the application in order to map like global terrain or canopy height. And also we are introducing the novel approach using this kind of spatial temporal blocking from the spatial LiDAR to do this kind of global to local terrain modeling to actually enables local context into the local model. And we also produced the first uncertainty map of the terrain that we found is correlated with the vegetation cover and the steepness, but also maybe there's something that we can still explore. And the last thing is we have produced this 15 global land surface variables that are deemed to be supporting this global contrast indicator mapping, for example, lifestyle mapping or soil type mapping. Yes.
Okay, thank you so much, Yu Fong. Exactly on time. Just for the participants, if you have a question, you have to use the Q&A. You use the Q&A, you write your question, and after we finish with the second talk, we're going to come back and we're going to try to answer as many questions as possible. Without taking any more time, I call Leandro Parente and Maria Hunter to take over the second part of the seminar.
Thank you, Tom. Good afternoon, everyone. I'm Maria Hunter. I'm a researcher at LAPIG, which is a remote sensing and GIS lab in central Brazil. So I'm coming from a little bit further away today. And I'm going to present a little bit at the beginning about some of the formation of how we came to create this global 30-meter annual median vegetation height map. That's based on ISAT-2 data and machine learning. And then Leandro will take over and talk more about the specific modeling and some of the results of this product. Tom, please change the slide. So a little bit about kind of why do we care about vegetation height? And I think the first response that everyone comes up with is regards to estimating biomass and carbon stocks. But then when we think about, there's a lot of other interesting pieces with regard to forest structure, the ability to look at species richness, thinking about fuel loads and fire susceptibility and the effects of fire across varying landscapes. So these are all potential applications of vegetation height data sets. Please go ahead, Tom. So, however, up until now, really the existing products are focusing on the top of canopy height. There's at least 4 different global products, one by Peter Potapov from the GLAD Labs in Maryland, published the first global height map using more modern satellite LiDAR data in 2019. However, there was previous work by Michael Levsky that was published in 2010, if I'm not mistaken. But all of these focus on the top of the canopy, and this is really helpful in forest ecosystems, but there's open questions as per how applicable this is in non-forest ecosystems. Please go ahead, Tom. So when we think about non-forest ecosystems, of course, I brought my local example, which is the Brazilian Cerrado. And you can see that there's a gradient from grasslands through shrublands, through open woodlands to more closed woodlands until we get to really gallery forests. And typically what's been used in these forest ecosystems is the maximum canopy height or potentially a Lorry's height, which is a forestry term, which is a basal area weighted height. So that has to do with the diameter of the tree. And these really come from thinking about kind of the amount of wood a tree can produce and the amount of biomass that it has. This is really helpful, as I mentioned, for forest ecosystems, but there's open questions about how applicable it is in non-forest ecosystems. Please go ahead. So when we thought about non-forest ecosystems, we really thought about kind of a median height, which would represent the dominant vegetation mass. So at what height do we have most vegetation? So I like to think about kind of the local pasture ecosystems that we have here and shrubland ecosystems where we'll have sparse, large trees intermingled with a strong grass cover or shrub cover. And in that case, if you think about it, it doesn't make sense that you would be really focusing on the height of that one tree as opposed to the height of all of the vegetation around it. So looking at the median height, the idea is to capture that height of dominant vegetation and being less sensitive to variability, which the mean would be. Go ahead. So once again, kind of looking back at our spaceborne LiDAR data sets that Yufeng presented, with regard to ICESat, it's particularly helpful because it does have this individual photon component, that the information for these individual photons is available. Each one of these returns is spaced about 70 centimeters along the laser track, and they have an 11-meter approximate footprint size. So this means that instead of JEDI, which has a 25-meter diameter footprint, the illumination area is comparatively smaller, and also it's more frequent. So that allows us to look at a lot of this individual level variability. And as Yufeng also mentioned, it allows us to separate out these components that are all kind of merged together in the JEDI data set. So that was one of the potential benefits for using ICESat specifically. Go ahead, Tom. So specifically for this product, we looked at the ATL08 product. So this is the kind of highest level of pre-processing that has been done by NASA. And it allows us to separate out these 100-meter segments, the 20-meter segments, and then some information about the individual photons themselves. Go ahead, Tom. But the question remained, okay, we understand that this is likely applicable for ice. There's previous work that's shown it's applicable in forests, but we had an open question regarding these non-forest ecosystems and the extent to which this median height metric would potentially be applicable. So we went to the field. This is local to the state of Goiás. This is the Rio Vermelho watershed. And on the left-hand side, you can see kind of the coverage by ICESat in a single year. And on the right-hand side, we can see this basin is primarily covered by pastures. This is kind of within the central west region of Brazil. There is some savanna and forest cover. There's some crop cover, but really it's dominated by pasture ecosystems. I say pasture ecosystems, however, in Brazil, these are usually somewhat mixed. It's planted grasses, but mixed together in some cases with shrubs, with trees. I'll show you pictures in a second. Okay, go ahead, Tom. So we went to the field and we specifically looked at 40 points that had been labeled in pastures for at least 5 years following the Mapiomas land cover classification. We specifically did 4 transects, measuring the heights of grass, shrubs, and trees. And then kind of coming back after the field work, we were able to align these best with which specific path that we took, which specific transect that we measured, best aligned with the specific LiDAR data that was the ICESat data from that point. The results of this fieldwork and the data from this fieldwork are all publicly available and they're published on Zenodo. If anyone wants to kind of go back through any of these analyses or look at these specific data sets, it's all available there. Next slide, Tom. So another reason for doing this was beyond just questioning the extent to which the ICESat data was applicable to these more open ecosystems, but also to what extent did it need to be filtered. So there's previously published work that shows that it's better to use the points that are collected at nighttime or using the strong beam. ICESat has a slightly different setup in that they have strong beam and weak beams paired. The strong beam is approximately 4 times more energy than the weak beam. So this was something that we looked at in the field data. We looked at the season of the overpass. So whether it happened in the wet season or the dry season here in the Cerrado, whether it was collected by a strong beam or weak beam laser, and whether it was collected at day or night. And here you can see some of images from the field work, and you can really see the variety of what these supposedly pastureland ecosystems capture. So you can see everything from relatively open, like not a whole lot of grass, but some shrubs, to very much planted grass, to kind of a low grass cover with interspersed trees and palms. And these are all regions that are used as pasturelands. This top photo, it was likely adjacent to something with a little bit more grass. So we found that we caught a lot of edge cases. And part of that was by design. We had specifically gone out looking for places with a wider variety of median heights and top of canopy heights. Go ahead, Tom. So when we look at the 20-meter segment size, we find that it's not perfect, but we do find a decent correlation, and that it's specifically most important to also kind of filter for strong beams and potentially do additional filtering to really improve our results. Go ahead, Tom. Okay, so that's kind of how these are some of the filters that were used in order to kind of produce what the data set would be that would then go into the global short vegetation height product that LAPIG, together with OpenGeoHub, together with other researchers from varying institutions, kind of produced as part of this global pasture watch consortium. Leandro, go ahead.
Okay, thank you, Maria. And basically, I will continue. And my name is Leandro Parente. I'm a researcher at OpenGeoHub. And yeah, before start my presentation, I think it's nice to explain that the main challenge here that we kind of proposed ourselves to test, it's really how feasible would be to use this ISAT data to derive a more kind of meaningful metric for vegetation height for non-forest ecosystems. And another thing that it's also interesting is that the way that we are presenting here, it's actually the way that the work was conducted. So there was a lot of pre-processing and a lot of preparation for this data, as Yufeng presented. And this data, once it was prepared, I mean, like ISAT 2 data, we started testing different applications. And also Maria is starting evaluating that, and with the field work, we kind of realized, okay, how we can filter and effectively use that for try to do this modeling. And my part now, it's actually how we kind of operationalize that to produce the global maps that we are seeing here in the right side. So what we did was basically kind of a time series of 30 meter for the whole world, like annual time series. So from 2000 to 2022. So basically we have global maps from all this period, and I will show some insights about that. And addition also, we did the trend map that you see in the bottom, showing where we have negative and positive trends, significant trends according to statistical test, to understand where we have vegetation dynamics. So you can access all the details about this work in this preprint, and I will basically highlight the main points during my presentation. Next slide, Tom, please. So basically, we have this kind of big workflow here. I will split this in different parts. And before to go in this different box that we are seeing, it's also important to explain that the data it's uploaded to Zenodo, and currently it's under embargo due the review process. So we just submitted, actually we submitted a few weeks ago, the manuscript, And if you really, if you want to have access, and actually we advise you to test the product before the publication is out, you can just enter in this link and fill the form explaining how you want to access and a bit about the applications that you want to use, and we will share the data with you. So this is just a process that we doing now before the publication be out, and of course once we have the paper out, all the data will be public, including reference data and source code. So basically I will explain several steps of this workflow, so including how we filter the data, so there was a lot of filtering, and how we did a kind of a sampling design considering the magnitude of the ISAT data. It's a lot of training reference points and how we did that. So how we managed to run the models and what are the rationale behind the model. And I will show some of the results and some visual analysis of the maps. Please, next slide, Tom. So here, if you zoom in this part, this is actually the beginning of the pipeline, right? So there was a lot of ISAT data preparation. We did some field calibration considering the field work that Maria presented, and also different types of filtering considering the sampling design. And I will explain how we used some existing land cover map. So the time series produced by University of Maryland, the GLAD group. So with multiple years to kind of filter the points. Next slide, please. So basically, as Yufeng presented, the ISAT ATL08, the 20-meter segment, it's about 20 billion points. So and in this, every data entry in these billions of points, we have several properties, including the number of photons that basically represent different kind of vegetation, returns, and terrain. So basically, we used these photons that were returned to compute the median height, and we did several filters here, like strong beam acquisitions during the night, minimal number of vegetation and signals, and things like that. So we explain in the detail in the publication, but the key message here is we still applied a lot of filters even after using this ATL08 product. Next slide, please. And so, okay, these 20 billion points, it's actually like way more data that we can use to train the model. And basically and also it's a bit like with different distributions all over the world. So what we did basically a kind of a random sampling, but a kind of a stratified random sampling for each month and tile. And when I mean tile, it's 1 by 1 degree. So we tried to keep some kind of regularity in the training data, in the reference samples, to kind of cover different landscapes of the planet. And also we considered the month. So we took like all the multiple observations across different months to actually also address the seasonality issues of different vegetation landscapes. Next slide, please. So another key process to filtering the points is basically our sampling design selected about 32 million points. And that's what we see here in the bottom of this table. And all these points, of course, they are located in different parts of the planet. And what we did, we took what we for each of these points, we just retrieved what is the land cover according to the GLAD map. And if you think about this, here you can see all the land cover types. So most of the points are located in dense short vegetation, like between 79 and 100% coverage. And what we see here is basically what is the average value of the median height. And so one message that it's important to pass here is if you go for places where we have stable tree cover according to the GLAD map, so and you can see that they also have this height information that they derived with their product for forest mostly. You have like areas between 20 and 25 of canopy, top of canopy, but the median height according to the ISAT, it's about 8 meters, like the average of all these samples in this stable tree cover. So we also was trying to understand, okay, how we can use this information and derive the median height, and how this is related with the land cover. Next slide, please. And basically we did like a lot of filtering. We removed some outliers according to this analysis. And another thing that we also did, because the ISAT doesn't cover heights that are lower than 50 centimeters, basically everything that was, all the samples that were on true desert, we just assumed like a very, like a height that was close to zero, some minimum detected height according to the data format that we were mapping. So this was a kind of a zero height imputation that we used to actually cover the limitation of the ISAT data. Next slide, please. So from the modeling pipeline, so basically we did all this pre-processing and we prepared the data. So we are talking about 32 million of reference samples with height covering vegetation height, median vegetation height, covering 4 years, 2019, 20, 21, and 22. And basically, we used a machine learning pipeline to model that, and a different set of Earth observation data. Next slide, please. So the main input for this product was the Landsat cloud-free bi-monthly aggregates. So with this DOI, you can find the publication. The data is also open available. And the thing here is we use it not kind of annual Landsat aggregates. Here we use the bi-monthly aggregates because we were eager to try to basically show the kind of seasonality and address this. Next slide, please. And basically, we model this with the light GBM, and here you can see the key parameters. So we use like a Poisson loss function, 20 iterations at early stop, and between 35 and 40 trees. Next slide. So also we did the we used 10 models, and with these 10 models, so 10 light GBM, we derived the mean, percentile 95, and percentile 5. Next slide, please. So I will pass through the results. So as I said, we derived this for annual maps, and here you can see 2000 and 2022. Here you can see some dynamics, and we can analyze that. Next slide, please. One more. And basically, this is our accuracy. So we had an R square of 0.51, and the root mean square error are 2.3 meters. So for this type of metric, basically the proper metric is the D2. And here we estimated that with the holdout validation, considering 10% of the sample, so 3 million of samples. The most important variables, as expected, it was the Landsat data. So May and June, red band, blue band, but we also used some MODIS temperature, land surface temperature data. Next slide, please. So basically here we can see the relation of the ISAT and the predicted mean. So we have different vegetations heights. So we can see that the stable tree cover, the median height, for example, for stable tree cover between 3 and 5, according to GLAD, it's pretty close to what we see with the median height in the ISAT data, and also in what we are predicting. So as Maria showed, we can also see that our heights are really close to the ISAT, and compared to other products, we actually cover a range that is not covered for most of the products using these kind of grassland reference areas. Next slide. And as I said, we have a time series, and you can see here the prediction interval, so positive, negative trend. So here we can see the negative trend when there was some deforestation across between 2010 and 11, and you can see like a positive, the negative trend, and the positive trend, just a kind of a regeneration process in two very close areas. So it means that the product is able to capture these dynamics. Next slide. And also it's important to explain that this is not, as Maria show in the beginning, this is not like the top of canopy. That's why we are calling this like a short vegetation height product, where we are mapping the median height. And with that, basically, if you correlate with the JEDI, you can see that the JEDI covers like a very different range of vegetation, but it's basically because it's measured top of canopy while we are measuring the median height. Next slide. So basically, the main takeaways are, I think it's mostly true. So we demonstrated that the ISAT data is a useful source of reference samples, but requires a lot of filtering steps. And also we can see through the maps that we are able to capture various spatial temporal vegetation and land cover dynamics, the vegetation loss, restoration, and things like that. But we are still working a kind of independent validation that it's not relying on ISAT data. So currently we are establishing independent validation strategy, collecting feedback for the current maps, and reevaluate the method to derive, for example, the predictions interval that current are too narrow and a bit over optimistic. Next slide. So here, as I said, you can access the maps, and also we are receiving feedback in our GitHub. So the source code is there, and more like technical information about the product. And yeah, I think here I finish my presentation.
Thank you so much. Thank you all the presenters, and thank you also for being on time. We are looking now for the Q&A. I see that some people ask already questions. I just want to emphasize one more time, if you access this data, especially the median vegetation height, so don't be confused. It's not the canopy height. You cannot use it to match, let's say, some ground data if you have on the, especially for the forest areas. So it is a very, very different data set, even though visually, when we look at it, they look quite similar, but they're different data sets. So the floor is open for questions. I see question, Amani. The slides and recording of this session, they will be shared on the TIB. So the slides will be made, the whole presentation will be made available with the DOI, so you will be able to watch this presentation again. So there was no need to write anything down. Just subscribe to our channel so you can see when the video is finished. And I have a question for, let's say, Maria. Let's start with Maria. This framework, you developed, now it's for more focus on short vegetation, but there's many parameters from ISAT and from JEDI. So we could actually use the same framework and just plug in another variable and then build a model and probably produced using the same framework predictions. Is that correct? Just microphone on, please.
Thank you, Tom. Yes, that is correct. And in fact, I think we already have a number of potentially useful metrics, at least calculated based on these photons from the ISAT-2 data. So part of the field work that I didn't show here today was kind of looking at some of these other metrics, specifically one that's really promising would be an estimate of fractional cover, which is really helpful for a number of applications. And then another thing that we're really interested in looking at is kind of the number of layers of vegetation and how that could potentially be helpful for some of the fire dynamic science.
Okay, here
but
we
yes,
have a question.
definitely.
We have a question about this median height, focus more on short vegetation. Question by Said. What is the accuracy for croplands?
So for croplands, what we see,
especially considering that there are cropland cycles, the harvest cycle and growth cycle.
So what we've seen for kind of plant, we haven't looked specifically at croplands, and that's something that we would love feedback on. When we've looked at planted pastures, which also have some of these cycles, We do see, like for this specifically, we're looking at the annual expectation. So another limitation of the ISAT that, at least for the way that we've currently processed it, is that vegetation is identified only at greater than 50 centimeters height. However, when I've looked at kind of the potentiality of using some of the photons that are identified as terrain, which have less than 50 centimeters, and included those in some of the vegetation analyses, that has been a promising kind of avenue for future use. My expectation is that we would really need to go through and look at some of this more annual cycling to see if we're able to capture that. As currently, we've aligned things temporally in order to try to best use the training data that we have, and the time period that the Landsat imagery is from for these predictions. But we would need to look more closely specifically at what they're pulling out for cropland ecosystems. But from looking at the data and looking at the maps, we are able to separate different fields in certain cases. But we don't really have the data in hand to say, oh, this is this crop versus that's that crop.
In the paper, you do have a table with the different land cover groups and what the accuracy is, right? So
yes,
it's possible.
Yes, definitely.
And just one last question for Leandro. So in the first talk we had, this Yufeng was building like a local models for like something like 1,000 local models tile by tile, and in your case you did a global models. But do you think if you had also some local to global, so you build many local models, you think is that suitable also for modeling short vegetation height?
Yeah, that's a good point. And so considering the ISAT data that we have available, we could definitely use something like that. And the thing is, we need to see if we would have like some gain in accuracy, because what we do now is we have these global models, and we use also some kind of covariates features that are able to capture like climate and like variations all over the world. So if we move for kind of a combined local and global model, we need to see what is the gain accuracy and how much more complex would be the pipeline. So I would evaluate that. So considering the results that we have.
With this thing, we're going to stop. Thank you. Thanks to all the presenters. Tomorrow, another interesting webinar. Please, if you're interested, join. You need to register. Thanks to all the presenters, and I wish you all the best with your research, and all the participants of the webinar. Just stay tuned for the video recording where you can watch this presentation one more time. Bye-bye. Bye-bye from OpenGeoHub.